Hey guys, okay, so we have a couple things to talk about really quick um, in this video. So you'll see there's two things in this video we need to talk about. So um, Q versus K. So we haven't really talked about what Q is yet and how to compare that to K. And then we need to talk about this, which is Le Chateliers. Um, so they kind of go together, and I'll try to make this short, but we'll kind of go through both these two topics here. Um, so first topic to talk about is Q and K. So you guys already know what K is. That's the equilibrium constant. So that's simply we use for any system that is at equilibrium. So any system that is at K is at equilibrium. Um, Q, which is the reaction quotient, is basically just the symbol we use for any system not at equilibrium. So if something is at Q, it's any system that's trying to get to equilibrium or has been stressed from its equilibrium, etc. So basically, you just need to know that K means that it's at equilibrium, Q is something not at equilibrium. But beyond that, there's not a whole lot of difference really between these two. Um, so kind of looking at them the way you guys have seen it already. In the last video, you saw like here's how you figure out K. So you have this reactant A that's, or sorry, this product A that's going up, and these reactants B and C that are going down, and then they get to this point right here where they level out and they're at equilibrium. So these are K values. Well, over here, the system's not at equilibrium because these are still trying to get to that stable point. So over here, this part is at Q. You'll notice the expressions for these are exactly the same. It's just that, like expression-wise, this part right here represents this section of the graph. So this is K, and then Q, this guy right here, represents this part of the graph. Um, all of this section where it's not at equilibrium, if I were to take any point here, like this point right here, this point right here, and this point right here, and plug those into this expression, then I'd be solving for Q. If I were to take the points here and plug them in, that would solve for K. So it's just, am I solving a system at equilibrium or am I solving a system not at equilibrium? That's the only difference between Q and K here. Um, so there's a lot of reasons why we need to know both. Like sometimes you just don't know what the system is, so you need to like calculate it based off of what the system's currently showing you, and then you can figure out if it's at equilibrium or if it's not based off of the value you get. Um, there's also some benefit too, just knowing, hey, here's where the system is right now. Where is it going? Um, so like if I were to plug these values into Q here, I will get some value for Q. If I know what the value of K is, then I know how this system is trying to get from here to here. So that's what comparing Q to K is. So basically, there's two options. If you solve for Q and you realize that Q is way bigger than K, so Q is greater than K, well, what we say there is that this reaction needs to shift. It needs to move so that the values here will end up calculating to the same value, not the same values, but the same overall value as here. Um, so if Q is greater than K, then we say that this reaction needs to shift left. It needs to make reactants. So that means that on a graph, the reactants will need to increase and the products would need to decrease. This is showing the opposite right now, but um, we'll kind of talk about that. So if Q is greater than K, it needs to shift left. And if you put it on a number line, here's where K is, and you know whatever the number for K is, and you solve for it and you get some number for Q, and you realize this number is greater than this, well, the Q is trying to get to this point. So it's trying to go this direction. So it needs to shift left. And that means that in a reaction, we need to follow the leftward arrow. The reaction needs to go and use the products to make more reactants. Um, Over here, it's just the exact opposite. So Q is less than K. That means as a fraction, this fraction is smaller than this fraction, which means that our numerator is compared to the denominator is smaller than our numerator compared to the denominator here. So that means we need to shift right. We need to make more products. And again, if we put these on a number line, well, here's K in the center. So we just put K in the center. We put Q over here because it has to be smaller than K. And so it needs to go this direction. So this is telling us that this reaction needs to shift right. And essentially the reaction is going to follow the rightward arrow. The reactants, the concentration of the reactants needs to go down because they're on the denominator and that needs to become smaller. And our product, which is the numerator, needs to increase. And so that's what you're actually seeing here. Kind of getting rid of all those scribbles. Is here at the start of this whole thing, we have this product A and these reactants B and C. The beginning value here, Q has to be smaller than K because our products are going up, our reactants are going down. So we're making products and we're losing reactants. So this value is getting larger, this value is getting smaller over time, and that will eventually get us from here to here. It is shifting right. So it's following this set of circumstances. So that's pretty much all there is to Q and K. Q is just a snapshot of the reaction. Here's where we are right now, which is not equilibrium. And if we know this, and we know where equilibrium is, we know what we need to do to get there. So that's all that goes into Q and K. It just kind of talks about what this reaction needs to do. And you'll notice we keep using this word shift. So this all ties into this, which is Le Chatelier's principle. So if a stress is applied to a system at equilibrium, the position of the equilibrium will shift in the direction which reduces the stress. It sounds like a lot, but basically what it's saying is you have some system at equilibrium. Okay. And all of a sudden something is done to this equilibrium. So you're doing something to this value which causes it to change and is not at equilibrium anymore. It's now at a Q. What Le Chatelier's is saying is that this Q value will do whatever it needs to do to get back to being K. A system wants to be at equilibrium. And so some stressor is applied to an equilibrium that causes it to be not at equilibrium, assuming that that stress is no longer there or not currently still being stressed. Like once that stress kind of goes away, this Q will do what it can to get back to being a K value. So we'll kind of look at this. So here's this reaction. Hydrogen gas is reacting with nitrogen gas to make ammonia. So products are reactants right here, and this is the same expression for both K and for Q. So it doesn't matter. This is the expression for K or Q. It just means that if the values I put in here are at equilibrium, I solve for K. If the values I put in here are not at equilibrium, then I solve for Q. So let's look at this. So initially, this system is at equilibrium. So all these are nice equilibrium lines. So Le Chatelier says if we apply a stress, this needs to happen. So the stress in this case is us adding H2 gas. We're going to add more of this stuff. So we're at equilibrium, and all of a sudden we're going to add more hydrogen gas. So all of a sudden there's just going to be a lot more hydrogen gas, and we get like up to here. So that right there is our stress. We added a reactant to this equilibrium system. So boom, right here, there's the stress. We added a reactant to the system, and now this value is now up here. It's no longer at equilibrium. So we're at equilibrium here. This right here is Q because we're not at equilibrium anymore. These values don't equal K anymore. So we added this stressor. This system is now trying to shift to get back to being in equilibrium. And it's going to shift in the way that makes that possible. So here we added this right here. So it needs to shift in such a way to make the system go back to equaling K. And so to do that, since we added this reactant, the reactant value is now too large. So these reactant values need to go down. N2 is also a reactant, so that value needs to go down, and our product needs to increase, and then we get back to being a K. So this right here is also a little too big there. This value right here is also a K. So we're at equilibrium. We get stressed to a Q value, and then that Q value over time goes back to being a K value. You'll notice that this new K, the lines here don't match up to where it was before. So these values here are not the same as they were over here, but all together, these values still equal this value. So even though these are different individual values, the K value itself is still the same. If I were to calculate this K and this K, they're going to be the same number. It's just that I'm using different numbers to get there. So the two fractions end up equaling the same thing, even though I'm using different values in each fraction. It's like saying 1 over 4 is the same thing as, oh, sorry, that's 1 over 2. It's like saying 1 over 4 is equal to 2 over 3. Or 2 over, man, I can't think right now, 2 over 8. So even though these values and these values are not the same, they end up equaling the same thing. This K and this K are the same number, but the values here and here are not. Okay, so that's a lot of me just explaining the same thing over and over again, just to kind of hope that it sinks in. So again, both of these are K values. They use different values here, but they equal the same number. Okay, so we talked about a stress being applied here. There are 5 different stresses that can happen to a reaction. So we're going to talk about all 5, and essentially Le Chatelier says if this happens, here's what it's going to do. So Le Chatelier is kind of just like a rule of thumb system. So we can just kind of use it as like, oh, this happened. We know how it's going to like adjust based off of that. So the first 2 stresses we'll talk about is adding chemicals and removing chemicals. So adding chemicals is what we just did. So here we added a reactant. We added this guy, and this. So the stress was adding a reactant, and our shift was the reactants went down and the product went up. So we shifted right. We shifted to this side of the reaction. So if we add chemicals, if you add a reactant, the reaction shifts right. It makes products. If you add a product, the reactant shifts left. It makes reactants. So anytime you add chemicals, it's going to shift to the opposite side of whatever you added. So we stressed it by adding reactants. Then that means that the system will shift right. The reactants will go down. The product will go up so that we can get back to equilibrium. If we add a product, then direction needs to shift left. The products need to go down and the reactants need to go up to get back to equilibrium. So anytime you add chemicals, it shifts to the opposite side of whatever you just added. If you remove chemicals, it does the opposite. It shifts to the same side. So if I remove a reactant, the reaction shifts left. It shifts to the reactant side. So I lost reactants. So I need to use some of the products to make more reactants to replace sort of some of what was lost. If I remove a product, it needs to shift right. So adding chemicals shifts to the opposite side. removing chemicals shifts to the same side. So if I remove a reactant, I shift left to the reactant side. If I remove a product, I shift right to the product side. Um, and so you kind of did some of this in that straw equilibrium lab that you guys did. So hopefully you guys kind of saw things like this when you got your data, where you saw these spikes up or spikes down in your data. If you didn't, then um, you probably just did something weird with your data, and um, you're welcome to kind of ask us questions about that and like see if we can't figure out what you did wrong or whatever. Um, but hopefully you did see these kind of spikes. Down here, you'll see this little thing right here that says catalysts have no effect on K. We haven't really talked about catalysts a whole lot, but the few times we have, catalysts are just there to speed up a reaction. That's all they do. So they don't change where equilibrium is. They just make things go faster. So if you do end up seeing anything about catalysts, just catalysts don't really apply here. They just make things happen faster. Okay, so our third stress is pressure and volume. More precisely, our third stress is pressure. Um, it's just that pressure as a variable, it's not something that you can change. You can't just look at a container and be like, okay, start being at lower pressure or start being higher pressure. You have to change something else to change pressure. There's no way to change pressure directly. So really, anytime you want to change pressure, you change the volume. Hopefully you guys remember back in gas laws that like if the volume were to go down, then pressure goes up. They have an inverse relationship. Um, so anytime I want to change the pressure, I just do it by changing the volume. So if I want to increase the pressure, that's this guy right here, the way I did that was by decreasing the volume. So if I increase the pressure, really what I'm doing is decreasing the volume to get an increased pressure. Because both of these are gas law related things, this stress applies specifically to gases. So the reaction is going to shift to whatever side of the reaction has the least amount of gas. So if the pressure goes up, it's going to shift to either the reactant or the product side. It just depends on which side has the, the lower number of moles of gas. Um, and I'll show you kind of more what that looks like on a later slide here. But so this one isn't going to necessarily shift left or right always. It depends on the reaction itself. You have to see which side of the reaction has at least the lower number of moles of gas on them. And that's the side you're shifting to if the pressure goes up. If I decrease the pressure, which means that I increased the volume, so I made the container bigger, so pressure went down, the reaction shifts to the side with the higher number of moles of gas. So this entire thing is gas related. So you're focused on the gases. So even though aqueous species like might be part of this, this is specifically what we're looking at here is how the gases react to the stress. So that's stress number 3. So here's kind of an example of that. This is, look, the exact same chemicals. So hydrogen gas, nitrogen gas, and ammonium gas. So this is the system at equilibrium. The volume goes down, so the pressure in this container went up. So here, the pressure just went up. So the pressure decreases, and now we have a new equilibrium position. Well, over here, we had, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. We had 11 of these guys. We have 1, 2, 3, 4 of these guys. Did I count that right? That must be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yeah, 12 out of 11. We have 12 of these guys at the beginning, and we only have 1 of these. At the new equilibrium, we have, I'm going to make this green. At the new equilibrium, we only have 3 of these things left. We only have 1 of these left, and we now have 1, 2, 3, 4, 5, 6, 7 of these. So when the pressure went up here, this thing shifted this direction. We ended up making a whole lot more of this, which we can see here, and less of this. The way that I knew that was going to happen, clearing all this writing here, is the pressure went up. Since the pressure is increasing, it wants to shift to the side that has the lower number of moles of gas. Well, in the reaction here, there's 3 moles of this and 1 mole of this, so a total of 4 moles of gas over here. Over here, there's only 2 moles of gas here. So if the pressure goes up, since our pressure is increasing, it wants to shift to the side that has the lower number. So it wants to shift right in this case. So going back, again, it's not always going to shift right or always going to shift left. It's always going to shift to the side that has the lower number of moles of gas. And we can see that just with the coefficients. There's 4 total coefficients for gases over here. There's a 2 total over here, so it shifts to this. If the reaction was flipped, it would shift the other direction. And this is the pressure increasing. If we were to do this the opposite way and instead make this container bigger, well, then pressure would decrease and we would shift the opposite direction and we'd shift towards this 4. So pressure, we're just counting up how much gas is on one side, how much gas is on the other, and depending on if pressure is increasing or decreasing, we're shifting to the smaller number or the larger number respectively. Higher pressure shifts to the smaller number, lower pressure shifts to the larger number. Okay, and the last 2 stresses to talk about here is temperature and dilution. So temperature, it depends on if the reaction is exothermic, if it gives off heat, or if it's endothermic, and the reaction absorbs heat. But really, if it's exothermic, we treat heat as a product. If it's endothermic, heat as a reactant. And then this just goes straight back to number 1 and 2. So once we know if heat is a product or a reactant, then we just we treat heat as a product or a reactant respectively. And it's the same thing as adding a chemical. So if it's exothermic, that means heat is a product. So if we increase the temperature of an exothermic reaction, well, if we go back to this, adding chemicals, if heat is a product and we're adding a product, so if heat is a product and we add more heat, well, we just added a product, so it's going to shift left. If it was endothermic, heat would be a reactant. We would be adding a reactant and it would shift right. So for the heat thing, temperature, you just treat it as a product or reactant depending on if it's exo or endothermic. And then it's increasing or decreasing the temperature is the same thing as adding or removing a chemical. Or if it's a product, we treat it like adding or removing a product. If heat is a reactant, we treat it like adding or removing a reactant. And then dilution, diluting a reaction or product will decrease the number of moles. This will force the reaction to shift in that direction. So this is sort of similar to removing a chemical, but if we dilute something and it only affects one side of the reaction, it shifts to the side that was affected. So if we have, reactants and products, again, anything in brackets means concentration. Wow, that's not the greatest writing on my part, but so we have this system in equilibrium. If all of a sudden the concentration here were to get really small because we diluted this side, well, then this thing would no longer be at equilibrium. And so it would want to shift to the side that just got affected. So I'm trying to write this out. So here you'll notice R gets really small because we dilute R. So that means it wants to shift this direction. We'll shift to the side that just got affected, um, if you can see in all my wonderful chicken scratch. So that's all that happens there. So those are the 5 different shifts. So we'll kind of look at each one here. So example 1, predict the direction of the shift of the equilibrium position in response to each of the following changes. So we're adding carbon monoxide. So that's this guy right here. So we add carbon monoxide. So we are adding a product. Since we added a product, it's going to shift to the opposite side. So this thing shifts left. That's it. So if we add carbon monoxide, we shift left. That means we're going to make more reactants, lose some product. If we add or remove tetraarsenic hexoxide, so this guy right here, if we add it, well, that's the same thing as adding a reactant. If we add a reactant, we shift right. So addition is going to shift right. And if we remove it, well, anytime you remove a chemical, you actually shift to the same side as what you just removed. So we'll actually shift left, so removal shifts left. So add this guy, we shift right. If we move this guy, we shift left. And then if we remove gaseous arsenic, so this is a reactant, we are removing this reactant, so we remove this stuff, and anytime you remove a chemical, you shift to the same side, so this will shift right. So that's essentially all there is to the Chateliers. You say, hey, here's the stress we're causing. Based off this stress, this is what the system needs to do to get back to equilibrium. So that's example number 1. Example number 2. So predict the shift that will occur based off of volume being reduced. So again, if volume is going down, then that means that pressure needs to go up. So this is the same thing as increasing pressure. So for each of these, we need to figure out how much gas is on each side here. So if pressure goes up, we want to move to the side as the lower number of gas, the lower number of moles of gas. So here we have 6 moles of gas here and 0 moles of gas over here because this thing's a liquid. There's no gas on this side. So if the pressure goes up, it wants to shift to the side with the least amount of gas. So it's shifting that direction. Here we have 1 mole of gas and 1 mole of gas. So we have 2 total moles of gas for this one and only 1 mole of gas here. So again, it wants to shift to the side with the least number of moles of gas. So it's going to go that way. And then last but not least, we have this reaction down here. So here we have 4 moles of gas here and 4 moles of gas here. Again, if pressure goes up, it wants to shift to the side that has the least number of moles of gas. Well, we have 4 and 4. So that means that there's no shift. Nothing's going to happen because there's no side that has more or less moles of gas in this whole system. So it can't shift. There's no way, like going this way is not going to relieve that pressure. Going this way is not going to relieve that pressure. So nothing's going to happen. It's just going to exist still at equilibrium at a higher pressure. And that's pretty much it. So again, when volume and pressure are involved, we have to look at how much gas is on each side to decide which way it's going to go. Okay, and then example problem number 3. So this is heat. All right, so here this is endothermic. So that means that if it's endothermic, we get to treat heat as a reactant. So heat is over here as a reactant. And so if temperature is increased, that's the same thing as increasing a reactant. So if we increase our reactant, we shift to the opposite side. So if we increase the reactant here, we go to this side. Well, this guy's exothermic, so that means that heat is actually a product in this case. So we can literally just write heat on the product side of this whole thing. Well, if we increase the temperature, we just increased a product, so that means we shift that way. So the top one, because heat is it's endothermic, heat's a reactant, it will shift to the product side. The bottom one is exothermic, so heat is a product, it will shift to the reactant side. So that's all there is to that piece of everything. All right, so here's a practice problem with actual numbers, and we can actually like see how Q and K work in this case. So the following balanced reaction has a K value of 0.057. So this reaction, we know what the K value is for this reaction. Find the Q value and determine which direction the reaction will shift using these concentrations. So all of these concentrations right here are for Q. The system is not at equilibrium with these values, so these are all Q values. Like these, if we plug these in, they give us Q. So if you are feeling pretty confident, I would say pause the video and see if you can't solve this, and I'll throw the answer up in a second. If you're unsure of what's going on, I'm just going to talk through I'll talk through all the answers here in a second. So I would consider just trying to pause it and see if you can't solve it, but I'm going to throw the answer up here in just 2 seconds. So this right here is essentially what this looks like. So first we need the expression. So K or Q, the expression for this is O2 over 1. The reason for that is this guy's a liquid, and this is a liquid. Liquids do not show up in equilibrium expressions. So the only things that show up are aqueous species and gases. This guy is a gas. He's the only one that shows up in this expression. So really, K or Q is equal to the concentration of O2. That's the whole expression in this case. So that means if all of these values right here are for the system not at equilibrium, well, that means it's just Q. It's this right here. So Q is equal to O2, so this right here is our Q value. There's not a whole lot worth calculating. Since we know where Q is, well, we throw a number line up here. Here's K. K is 0.057, and Q is 0.57. So that whole extra zero right here matters a whole lot. So Q is way bigger than K. It's almost 10 times bigger than K. Q wants to get to K, so it wants to go this direction. So this reaction needs to shift left. So to do that, that means that our O2 and like these concentrations need to go down, and this concentration needs to increase. We're making more of this. All right. So I want to give you guys a good visual too for this whole Chatelier's thing. So like an actual reaction that does something, and like you can see it shift back and forth. This is the reaction that works really well for this because on this side you have this chemical right here that is a nice pink color, and on this side you have this chemical right here that's a nice blue color. So you can see it shift between pink and blue. So if you type in this tiny URL right here, it will pull up a YouTube video. We didn't make this YouTube video, I just found it because it does a really good job. This is all the stresses that he goes through in that video, so I definitely say watch that video. And you'll see the test tubes bounce back and forth between these colors as he does this stuff to it. That being said, I'm going to talk through each one, just so you know, like why is it bouncing to pink or why is it going to blue, etc. But I definitely say watch this video so you can actually visually see that happen because it's actually a pretty cool reaction. So definitely watch this if you have a chance, but we'll talk through each one. So stress number one is adding HCl. So we're adding hydrochloric acid. Well, you can see that HCl isn't anywhere in this reaction up here, but Cl minus is. So if we add HCl, it's the same thing as adding Cl minus because this thing breaks up to make Cl minus. So really what we're doing is we're adding Cl minus. So this thing should shift this direction. So that means that test tube should go from being a pink color to a blue color. And so that's the shift we see. We see it shift right and it becomes blue. Um, so it's if it's like perfectly in the middle, it's a purpley color. Um, Usually this reaction starts off more pink or more blue. Um, and then you can shift it right by adding HCl. In the video, he grabs a fresh test tube, that starts off pink, and then he adds CaCl. Oh, there should be a 2 there. Oh man, come on, Char. So he adds this, which is a solid. So he adds some little pellets of calcium chloride. Well, calcium chloride has chloride in it, so he's adding chloride, and boom, it shifts this direction. So you also see that because we're adding this reactant, again, it shifts to the opposite side, so it shifts right. And this one's actually really interesting because he's adding that pellet. So the part of the test tube that actually changes blue is the bottom part where all those pellets are, because that's where all that calcium, the calcium chloride is. Again, there should be a 2 there because I typoed. And so the blue color actually stays only near these pellets. The top of the test tube is still pink because that calcium chloride hasn't gotten to the top. So it actually hasn't changed the concentration of Cl minus at the top of the test tube, just at the bottom, which is kind of cool. From there, he grabs I just threw it up before I meant to, but from there, he grabs a blue test tube. He grabs one that is way more of this, and he adds water. So he's adding this product, which causes it to shift this direction. So he adds a product which shifts left, and so it shifts left and becomes pink. So that blue test tube goes to being pink. So honestly, he could have just used this test tube from number one, added water to it, and shifted it back to being pink. And you could just keep using the same test tube, and so long as you still have room in that test tube to add stuff, you could bounce back and forth between the 2 different colors. So that's what happens there. And then from here, the next thing he does is he adds um, this right here. So he adds silver nitrate. Silver nitrate reacts with chloride and it removes the chloride from the solution. So what he does with the 4th test tube is he starts with a bluish test tube here, and he removes chloride. So he's now removing this thing. Well, anytime you remove a chemical, it's going to shift to the same side that you just removed things from. So the blue test tube now shifts to being a pink color because it's shifting this direction. And then last but not least is adding heat. Well, you'll see he starts with a pink test tube. He adds heat. Well, heat is right here on the reactant side, so he's adding a reactant. That's going to shift this direction because you're adding a reactant. It shifts the product side, and so it shifts right and makes a blue solution. So that was a lot of rambling on my part because I just know that this is a confusing thing, and it's especially hard since we're not like physically in the same room for you guys to ask questions and everything. It's a lot of kind of practice with this stuff. Um, there is another video. This is done by, again, our channel called Bozeman Science. So this video right here, it's only 7 minutes long. He goes through the Chatelier's principle as well. So if you're still confused, definitely watch this video. If you feel like you just need a little bit more support or another kind of way to talk about this or visualize this, definitely watch this video. So that is it for me. We'll talk about this whole thing kind of throughout this week here, and let us know if you have any questions, concerns, what you feel like with all this, and I will leave you at the 40-minute mark. I'm sorry this is so long, but we are at the end. So thank you, and please have a lovely rest of your day.